which I forgot to do last time. Okay, and now I'm going to switch over to my document camera so we can go through that worksheet that I posted online for you guys. So this topic is called volume with a known cross section, and I'm going to have to try and draw things, and you guys know what a great artist I am, so you're going to kind of bear with me on this one. So these problems sound a little bit different. This one says the base of a solid is the region enclosed by y equals x and y equals x squared. Okay, so that part I can do. I can draw a graph of that. So let's do that. Here's my xy axis. X, y, here's y equals x. Here is y equals x squared. That's a parabola. So I've got this kind of parabola shape. Right here is the point 1 because they intersect at 0 and 1. And so we're talking about this area right here. What this problem is saying is that that region, that kind of crescent-shaped region, is the base of a solid. So it's the bottom. It's like if I'm standing above some shape, that's what it looks like when I'm just staring down at the top of it. But then it says that cross sections perpendicular to the x-axis are squares. So that's where we're starting to talk about volume and trying to make this thing 3D. So what we're saying is that this shape right here, this is like the flat bottom, but there are slices sticking straight up from that. So I'm going to try and draw a three-dimensional drawing. So this is going to be interesting. So I'm going to draw this at a slant. Here is my y-axis sitting at a slant. Here is my x-axis sitting at a slant. You can imagine those kind of just being flat on the ground. Here's that shape that I just drew. Here's y equals x. Here's y equals x squared, right? And that's that base of the solid. I'm going to switch colors. And what they're saying is that if I slice through this perpendicular to the x-axis, the shape that it makes is a square. So there's my little square. You can imagine that square is sticking like straight up from the paper, like, oh, I just happen to have a pack of Post-it notes. It's like sticking straight up from the paper like these Post-it notes are. And you see how this shape of the Post-it notes is a square? Well, that's what's actually sitting there, is a square that's sticking straight up in the air. Okay, this is handy to have here. And so what they're saying is that anytime I do a cross section anywhere along this base, it's making a square. And notice how those squares are all different sizes. The length of that square is determined by the distance between those two functions. So this little line that I just drew right here in really bold would be this line over here on my drawing. It's that little slice of that drawing. And so I can look at this kind of flat graph of the base and know that that line that I drew on the base is the same as the base of that square. Okay, you guys with me so far? Seem all right? Okay, so if I'm trying to find the volume, so you can kind of imagine that I can split this area up into just a ton of these little square sort of tiles. And they're going to be really small down here at the bottom, and they're going to get bigger for a while, and then they're going to start getting smaller again. And it makes a shape that I'm going to say kind of looks like almost like a crescent roll sort of a shape, but it has corners on it. If you can imagine that shape, where it's like narrow at the ends, wider in the middle. So can you guys kind of picture what that shape looks like? Sometimes in class, I actually have you guys play with Play-Doh and make these shapes and build them to kind of get a visualization. So if you have Play-Doh at home, you could like try and build it. There's a fun little after school activity when you're bored and have nothing else to do. So anyway, okay, so let's get back to this. You can imagine each of these little tiles. I'm going to put a little width on this. And each of these little tiles, if I was to try and find the area of that tile, well, this is a square, right? How do I find the area of the square? It's just the length of the side squared. So because that base of the square is this area on the base of that, this object that I made, then I know that for that particular square, the length of its base is x minus x squared. Remember, that's kind of what we saw last time, where when we were trying to find the area between two curves, it's the upper curve minus the lower curve. This is not really in focus. Okay, that's a little better. And so this right here, this x minus x squared is the length of this blue line right here. Now, since it said these tiles are squares, I know I can find the area of that square just by squaring it, right? So that x minus x squared would give me the area of the front of that little square right there. But if I'm trying to find volume, I know that that square has a width to it, which means whatever that little width, we'll just call that delta x, is the width of that square. In order to find the volume of this, I need to add together all of those little tiny tiles. How do I add together a lot of little things? Well, I integrate them. So I'm going to go back over here and say, if I'm trying to find the volume of this, I'm basically going to add together all those tiles. I'm just calling them tiles for the sake of a language for them, which is the same thing as saying I've got all of these squares. Each square has a face that's x minus x squared squared. It has a tiny little width on it that we're going to basically make 0. And I'm going to integrate it from the intersection points for the shape. So they intersect over here at 0, they intersect up here at 1. And so what I'm essentially doing right now is taking every single one of those little tiles that has a face that's a square and a tiny little width, and I'm adding them all together by integrating from 0 to 1. So I'm going to put a hold on that for just a minute and talk about, in general, what does this mean that we're doing? What the idea behind all this is that if I'm trying to find the volume of some sort of three-dimensional object, that is equal to the integral of whatever formula I have for the area of each of those individual slices. So since this was a square, we use the area formula for a square, and I'm integrating the area in between those boundary values. And when I integrate area, what I'm left with is the total volume of that object. So this is kind of our key idea right here and what we're talking about in terms of how do I find the volume of a three-dimensional object. It's taking the area. If I were to slice it up into those little pieces, how do I find the area of each of those slices? I integrate that area, and what I'm left with is volume. So on this one right here, okay, I'm just going to hang out for just a second. Are there any questions that are popping up right now that you guys want to ask before we keep moving on? Or are we doing kind of okay? We seem to be kind of okay. All right. Okay, so now this, again, I'm not going to spend a ton of time integrating it. This is a x minus x squared, so you could multiply it out and integrate it, but we've already said, hey, it's okay for us to use our calculators, so I'm probably going to go ahead and use my calculator to evaluate it. I saw that there was some chat. I'm gonna stop sharing this for just a second so I can see chat better. It looks like it could be a banana. This is true. Oh, I'm still confused about how we got x minus x squared. Okay, so if I go back, let's go back to the drawing. I'm going to go back to my screen share. If you remember last time when we were finding the area between the two curves, that's basically what I'm doing right here. Is I'm trying this blue line right here is a piece of that area between these two curves. This upper curve right here was formed from the line y equals x, and the lower curve down here is the line y equals x squared. So the distance between those two lines is the difference between those two. So the length of that blue line, is just the distance from the upper curve minus the lower curve. And so the upper curve was just the line x, the lower curve is x squared. So that's the length of that blue line. But since we said that that blue line is the base of a square, and I'm trying to find the area of that square, a square is just its side squared. So that's why I took the length of that blue line and I squared it to find the area of that square. And we'll see, because the next couple examples, we get into other shapes as well. And so they're not always going to be squares. So maybe it might help that a little bit. Okay, so this one, again, like I said, I'm going to throw it in the calculator according to the calculations I did already, I'm going to get an answer of 0.0333. That's just a number I got off my calculator. So that's how we have on that one. Okay, so that's one that's a square. So let's move on to the next example, where it says the base of a solid, there's my doodle on my desk. The base of a solid is the region enclosed by y equals 4 and y equals x squared. Cross sections perpendicular to the x-axis are rectangles with heights half that of the side in the xy plane. So your first job is just to take the line y equals 4 and y equals x squared and figure out what that region is. So think about what that shape looks like. Maybe make a quick sketch of what you think that looks like. Of just the region, so y equals 4 and y equals x squared, because we have to start with that base. And we should always be drawing little pictures of these, because that's what really helps us see what we're looking at. So there's x, there's y. Here's my horizontal line, y equals 4. And y equals x squared, again, is a parabola that sits at the origin. So it's going like this. Y equals x squared. And it's the region in between those two. So I've got this shape right here. Now, before I go any farther, it says that the cross section is perpendicular to the x-axis. I'm just going to stop right there. So my cross section perpendicular to the x-axis. They're talking about if you were to kind of slice it right here, that's the base of a solid. Now, if I want to just come up with a mathematical expression for that, the length of that pink line, what would my algebraic equation look like just to find the length of this line? So we're not thinking about the rectangle thing, but how do I find the length of this line anywhere in the shape? You can type in your answer for what that length of that line is going to be. Good. Yeah. Okay. Exactly. Right. Remember, it's always the upper function minus the lower function. So that pink line right there, the upper function is the line y equals 4. Lower function is x squared. So that expression right there is going to be the length of that line. Good. Okay. But now we're talking about cross sections perpendicular to the x-axis. So I'm going to make one of my weird little graphs. I'm going to try really hard to do this. So here we are in the flat plane. There's y. There's x. Here's that horizontal line. Here's the parabola. So again, we've got this shape, looks kind of like, I don't know, an orange wedge, maybe, right? So that's flat. But then it says that cross sections perpendicular to the x-axis are rectangles with heights half the side of the side in the xy plane. So if this is the side that's in the xy plane, so this blue line right here is this pink line right here. It says it's a rectangle. So if I cut through, I'm making a rectangle. What do I know about the rectangle? It's half as high as it is wide. So I drew kind of a squat little rectangle to show that it's think of that blue shape as sticking straight up into the air. It's like coming out of the paper. It's a rectangle, but it's only half as high as it is wide. I could draw another one back here, which is going to be a smaller rectangle, still half as high as it wide. Down here, I've got a little tiny rectangle, but we've got all these little rectangles. So once I know the length of that side, my next thing I have to figure out is how would I find the area of one of these rectangles? Well, I already know the base because we said the base was that length 4 minus x squared. What's the height going to be? Well, it's going to be half of that same length. So I'm going to multiply that by 1/2 of the same expression, 4 minus x squared. Because here is the base, and here is the height, and it told me that the height was half of the base. Okay, so that's that area of that rectangle. Now, if we think back to what we did last time, and we said that the volume is going to be equal to the area of that slice integrated, that means for this one, I'm going to say volume is equal to And I'm just going to combine this stuff together. I'm going to do a 1/2, and since I have two 4x squareds, I'm going to write it like this, dx. Now, it doesn't, you don't have to combine stuff like that. We're really just looking for this sort of, excuse me, integral expression thing right here. But this represents the area of those rectangles. And I'm going to integrate it over the entire range. Now, what are going to be, I need to know what these boundary values are. What are my boundary values going to be for this equation? Where does x squared equal 4? Right, so we're looking for those two x values, that when I square them, I get 4, which is going to be x equals -2 and x equals 2. And we could solve that, you know, just do x squared equals 4. That's what we're trying to figure out. We are remembering always that square roots have two answers to them. And so my boundaries for this are going to be from x equals -2 to x equals +2. And so there's my intersection points. There's my formula for the area of that shape. And then I would integrate that guy. And according to the work that I did on this the other day, that ends up being 17.0667. Okay. Questions on that one? So what ends up being different on each of these is this description of what that shape looks like. The first one, it said they were squares. And so we use the formula for the area of a square. This one says they're rectangles, so I use the formula for a rectangle, which is base times height. The next one we're going to look at, that we can try and squeeze in real quick in these last couple minutes. It says the base of a solid is the region enclosed by the semicircle, the square root of 16 minus x squared in the x-axis. Cross sections perpendicular to the x-axis are isosceles right triangles with one leg in xy plane. Oh my goodness, what does that mean? Well, it means I have a triangle. What's true about an isosceles triangle? I know that both of the legs are the same height. So what they're telling me is I basically have a triangle that is isosceles, meaning the height and the base are the same height, and that this piece right here is the part that's in the xy plane. So it's going to be a triangle. So if we draw that semicircle, what's the radius of this semicircle? Yep, it's 4, right? The 16 minus x squared, that's basically us using the Pythagorean theorem. So that's 4 squared minus x squared. So this is going to be a semicircle sitting here, going from -4 to +4 and the x-axis. So I've got this round semicircular shape. If I draw my kind of three-dimensional, here's x, here's y, here's that semicircle that's flat. But then what they told me is that if I slice through it, so I slice right here, that's just the height of that curve, right? I don't have anything else going on. So I know the height of that line right there is just the value of the function. So it's 16 minus x squared. But over here, if I make that same slice in the xy plane, it says it makes a triangle, which means I'm going to have a right angle going straight up, and then it's going to make a triangle shape. Now, it's kind of hard to draw that in three-dimensional, but you can kind of imagine that I've got these triangles sticking up out of this shape. So it's actually going to come up to a point. I could draw another line over here, and I'm going to have a little triangle sitting right here. I can draw another one right here. And they're just making all these triangle shapes. So it's like it's going to have a flat side over here, and then it just kind of goes straight down. So my question again is, what is going to be the area of any of those triangles? Well, what do I know about area of a triangle? It's equal to 1/2 the base times the height. And this is isosceles. So what's true about the base and the height? Here's the base, here's the height. They're going to be the same. So this base right here is this purple line right here, which we just said was the value of the curve. So in this case, my volume is going to be 1/2 the base, which was that square root, 16 minus x squared, times the height, which is the same thing, 16 minus x squared. And then I would put a little dx in there because that's the depth of each of those little tiles that we're making. And then I know I have to integrate it, and it just says I'm integrating this circle, which we already said had a radius of 4, which means I know it goes from -4 to +4. So this square root times square root is just going to simplify out to -4 and 4. I can pull the 1/2 out in front. I've just got 16 minus x squared dx. Or like I said, you know, we're not super worried about the integration right now, so you could literally just put this in your calculator right now. And I'm going to end up with a volume for this particular shape, 42.667. It is volume, so it is some sort of cubic units. Generally on these problems, if they're not like a context-based problem, we don't have to worry too much about writing units on our answer, but it is volume. So if it gave you actual dimensions and measurements, you'd have to write your answer in like cubic inches or cubic feet or something like that. At this point, we're really just kind of concerning ourselves with finding that value and determining our volume from there. So our key idea here today, again, is just that idea that if I'm trying to find the volume of something and they tell me the shape of those little cross sections, I'm going to find some way to use the equations I have to find a formula for the area of those cross sections. Then I integrate that area, and the result of adding together all of those areas is going to give me the volume of the object in question. Okay, so that's our 3 examples. What kind of questions do you guys have? Comments? What do you think? We okay? Does it make sense? Give me a thumbs up if it sounds okay. Okay, good.
Why is volume integration?
What was that?
Why is the volume the integration of it?
Because what we're really doing is we're taking that object and we're breaking it into a bunch of little slices, little pieces, and stacking them all together. You can kind of think like as if it were like all of those, the squares, if they were all like tiles, ceramic tiles, that if we take all of those little teeny pieces of area and lay them next to each other, we've got all of those kind of 3-dimensional slices. And when we add the area of each of those slices together, it gives us the volume. If you think about like the formula for the volume of like a cylinder, how it was, you find the area of the circle and you multiply it by the height, right? We're doing exactly the same thing. That's exactly what we're doing, is we're finding the area and then we're multiplying it by the height. The difference is that we don't have like this in a cylinder, you have the same circle all the way up and down, right? But this, we've got a shape that's varying in size depending on what that graph looks like. And so I can't just do base times height. I have to find a way to vary the base depending on the functions. And that's why I have to use the algebra piece for the area. And then I'm integrating, and that integration is the part that is multiplying by the height of the object. Okay. So is that all the work we would have to show? Yeah, that's pretty much it. It's the sketches. It's showing a formula for the area, setting up your integrand or your integral with the boundaries on it, and then an answer. That's really all that we're looking for right now. When they did have these problems on the AP test, and like I said, these actually aren't going to be on the test this morning. Nice. A lot of the times they just say set up the integral. You don't actually have to integrate it. And so that's why I just wanted you guys to be able to get to the point where you're setting up the integral and then you can throw it in your calculator and be done. Okay, all right, well that takes us to my calculator said the boundaries for the last problem were invalid. Oh no. That's a good question. I don't know why. It worked on mine. Maybe make sure you use the negative and not the minus sign for your 4. That's the thing, the calculator gets really picky about whether or not you're using the negative as opposed to putting a -4. It won't integrate that properly. Okay, so that's the end of our time. I did post a worksheet into Google Classroom with a couple of problems like this for you guys to do and submit. If you haven't submitted the other homework assignments, that's fine. Just go ahead and submit them. I'm not marking anything late because I know you're not always in control of when you can be at the computer. If you are working on reperformances, you can just keep uploading those and I'll kind of be emailing back and forth to you guys about where we're at and what you need to be working on. So otherwise, that's it for today, guys. Thanks for coming in. Have a good rest of your day.
Thank
Bye.
you.
And
Bye.
I'll see you either office hours tomorrow or I'll talk to you again on Wednesday morning.
Okay.
Okay.